Hi students, it's Mrs. Cynthia again, and now I'd like to talk to you about section 2.3, gas behavior. Gases are pretty cool, and they behave in a very cool way. That's my introduction. The way that you want to think of gases, I hadn't thought of this before and then read your book, and I realized that was a great example. A sandstorm is a great way to think of the way that the molecules are interacting with your skin and your clothes all the time. So if you're in the middle of a huge sandstorm, you're getting hit with sand on all sides randomly. You don't know where it's coming from. It's just happening. It's like this big spiral. And that bothers you, right? Because it's sand, which is silicon dioxide, which is not, it's not fun. It's like glass. So hurts. But that's what's happening with gases all the time, okay? Gases are bumping off of you. They're hitting you randomly. It's constantly happening, right? So it's just a nice visual for how do gases move. One thing that you do need to know about gases is that the faster the gas particle moves, the faster a gas particle, I'm going to say. Again, that means either a molecule or an atom. The faster a gas particle moves, the more pressure they put on their container. I'm going to say put in a collision, just because if let's say that there is a gas particle, it's right here and it's moving kind of slow, it's going to bounce off of here definitely. But you don't feel it, and so that's why this is kind of a bad analogy. But the faster it moves, the more pressure it creates, the harder it is on there. And so, it's a bad example when it comes to that part, but because you can't feel them, but you know what I mean. Okay, so let's focus on a ball that's filled with a gas. Okay, so this one is partially filled. It's a basketball, and those are all of the balls, all of the molecules and atoms that exist in here. And as you guys know, the nitrogen, the oxygen. Okay, let's see what happens what happens to the ball when we increase the pressure. Let's look at how you can increase the pressure. So how can you cause these particles to move more quickly? Or any of those things. So this is a great video to really help us think about how volume and pressure and temperature are all related. So please pay attention to volume changes. Delta means changes. Temperature changes. And pressure changes, because they are all related when it comes to gases. So let's go ahead and look at this video.
The independent gas particles inside a slightly deflated basketball collide with one another and the walls of the basketball, causing pressure. How could you raise the pressure in the ball? You could add more air particles to the ball. As the number of particles increases, so does their number of collisions per second with the wall of the basketball, which first pushes out the walls of the ball and then raises the pressure. You can also alter gas pressure by changing the gas temperature. Warming up the basketball causes the gas particles to move faster. The faster moving particles collide more frequently with the wall of the basketball, causing a rise in pressure. As the gas pressure increases, so does the volume of the ball, until eventually the ball explodes.
Okay, one of my favorites, because it really is showing you exactly what is going on with the gas particles in relation to temperature and pressure. Okay, so let's summarize two of these relationships. Okay, the first summarized for us by Mr. Boyle. What he is saying is that as pressure increases, so let's go ahead and write that. As pressure increases. Okay, so the way that this is creating pressure is this is like a piston. This has a little bit of mass on it pushing down, but then you increase the pressure by adding another weight on it and another one. And what is happening to the volume? As pressure increases, volume will decrease. Okay. This can be seen in a reaction, or as you can also think of it this way, as volume increases, pressure decreases. Okay, so as one goes up, the other one is going down, and that means that it is inversely proportional. Okay, it's inversely proportional. So if we look at a graph, and pressure is here and temperature is here, what you would see is an inverse proportion. You would see that as one is going up, the other one is coming down. Okay, so that's kind of the way that you want to look at it. There is an equation for this. P initial, I always say P1, times V1 is equal to P2 V2. So this is saying that the pressure and the volume, the relationship between the pressure and the volume here is going to be equal to the product of the pressure and the volume under different circumstances. So if the pressure and the volume are such, and we'll look at an example in a second, and then all of a sudden they're kind of at equilibrium, so they're maintaining just like this, but all of a sudden I increase the pressure, what's going to happen to the volume? So if this is a number, if this is like 100, right, and I increase the pressure, so this goes up, because this is 100, this has to go down to keep this be equal to that 100. Okay, so if you rank which one has the highest pressure, this one has the highest pressure, which one has the smallest volume, this one has the smallest volume. Okay, so let's look at an example of Boyle's law and do a calculation of it. So, two questions. Let's say that a helium-filled balloon contains 125 milliliters of gas at a pressure of 0.0974. So you're going to see mostly ATM as the pressure unit, and then this is, of course, the volume unit. So if I look at my equation, P1 and V1 is equal to P2 V2. What I can do is these two are clearly together. This is the volume when the pressure is this. And so I can put them here as initial. I can put them here as final, as the second scenario, but they have to be together. So I'm going to go ahead and say 0.974. I'm going to keep my units because that's what we do. I'm going to multiply it by 125 milliliters. And I know that this is going to, the question is, what is the new volume if the pressure increases to 1 atm? So here the pressure is going to be 1 atm. ATM. And then I want to know what my volume is. So how do I solve this? I multiply these two times each other and I divide by this side. So let's go ahead and work through that. This is going to give me 121.8. The unit after I do this does not cancel out, so it's ATM times milliliter is equal to 1 ATM times the B squared. I'm then going to divide both sides by the 1 ATM. That cancels out that unit, and I brings over this unit. This ATM is now canceled, and there's no other work to do, so my new volume when the pressure is at 1 ATM is going to be 121 milliliters is the V2. Okay, and so that's what's nice there. Okay, so go ahead and pause this and do question number 2. I'm going to write the answer right here, but pause now. Okay, now you're on pause. So 0.77 atm is what the final pressure would have been, okay, or the P2 would have been. Okay, so that's Boyle's law. The other relationship was the volume and the temperature. There's a lot of other ones, but we're scratching the surface with these gas laws here. So Charles talks about another kind of scenario. Charles says he's a direct proportion guy, okay? Proportion. And his equation says this, that V1 and T1 is going to be equal to V2 and T2. So again, we have an initial scenario and then a final scenario. If you were to draw a graph for a direct proportion, as one is going up, the other is going up. So again, we have pressure here and we have volume here. As the pressure goes up, so will the volume. Whoa, but I'm not supposed to have pressure and volume. We're supposed to have temperature and volume. So this should be a temperature here. Sorry, my notes are a little off. So as temperature goes up, volume goes up, or you really could switch those. And so here is an example. It says draw the piston and gas particles when the temperature goes up. So here's no heat. All of a sudden you increase the pressure, the temperature, and so yes, the volume will go up. So here's your piston. The volume's up as you increase the temperature, and whoa, overflowing here. That would be what would happen, and the particles are in there. And let's go ahead and do one example. Oh, I didn't show you the video. You want to see the video? Let's look at the video. I forget which one. Oh, this one's awesome. Let's do this one in class, actually. I'm going to do that one in class instead. Oops, I don't even know what that is. Oh, Bill Nye. That's funny. Let's do this video.
Okay, we've got some liquid nitrogen, which is minus 196 degrees. Let's see what happens if we put that over an air-filled balloon.
So really, really cold, and so he's going to change the temperature of the gas inside here. And so he wants to show you what's going to happen when you decrease dramatically the temperature of all the gas particles in here. What's happening to the volume? So temperature is going down. The volume, according to Charles, is...
So the air's got really cold inside.
Going down.
Air, when it gets cold, gets smaller and falls down. Let's warm it up using the breath.
And then check this out. This is what I think is so cool, right? So now he's going to heat it up. He's going to heat up the temperature of the gas. And look at that. The volume increases again. So as temperature went up, the volume went up as well. I think that's awesome. Okay, and so go ahead and try this example using that same equation. There's a nice visual for that. And I'm going to tell you this is going to be in, the relationship has to be in Kelvin. This is another measurement for temperature. So 273 Kelvin is the same as 0 degrees Celsius. And so you have to do this calculation with the Kelvin. And so you would report it in Kelvin. So go ahead and do the calculation, and then I'll tell you what the answer is. Pause now. Restart now. The answer that you should have gotten was 364 Kelvin, and that would be the same as 91 degrees Celsius, so quite warm. Okay, and that's why the volume went up so much. Okay, so have a great day. Thank you very much for listening.